Three, two, one, you can start.
Hey, good evening, everybody. So I don't know how I can compete with Yifan's talk. It was one of the talks I was most disappointed in missing at Scala Exchange because I have a bit of a background in networks and distributed systems. So, but hopefully this will be entertaining and a little thought-provoking and of interest to you guys. So today, what I'm going to talk about is really when we're writing software, we all follow lots of rules. You know, those are rules about style, those are rules about how we structure code, those are rules about how we write code, like purity, you know, functional style, even OO is a paradigm and a set of rules about how and when we write code. So, but rules are an interesting thing because I found during my career that I tend to end up breaking them. But I break them in a very specific way, and I thought it was interesting enough to talk about. So let's start with a quote from the Dalai Lama. You know, so even the Dalai Lama knows that rules are made to be broken. So let's ask a simple question. Why do we write software? We write software fundamentally to solve interesting problems. And to do that, we have a really interesting toolkit. And one of the biggest tools and the biggest power tools we have in our arsenal is a modern CPU. So let's look back a few years to a little before my time, but not much. So in 1974, the TMS 1000, one of the first microprocessors was released, and this ran at 0.3 megahertz and had 8,000 transistors. Yeah. So a crazily big number. If we skip forward to 2018, we end up with a 32-core AMD EPYC, which runs at 3.2 gigahertz and has 19,200 million transistors. So let's put that in context, right? This is you know, nearly 2.5 million times more transistors and running 1,000 times faster. Pardon me. So this is insane. You know, when you look at this and you graph it out, it's just crazy. And actually, AMD have just released their newer EPYC processor, which now has 64 cores with even more transistors. But we have a problem. And the problem is, in my mind, a crisis. Software is fundamentally limited by our ability to reason about it. You know, the biggest problem in the entire system is something. It's not your computer speed, although some of you may think that when you open your laptop and try and do something. And certainly for me, it's me. It's the ability to reason about the code we're writing. So as we scale up, as we write bigger and bigger bits of software, there's only a limited amount of stuff I can hold in my head at any one time. And I'm sure the same as you. It's probably more than me, but it is still limited. So this is a challenge. How do we deal with this? Well, I need to take an aside for a second and go, what are we optimizing for? Well, we can optimize for multiple things when we're writing software. And I want you to think, next time you sit down at your keyboard, what you're actually optimizing for. Now, obviously, one of the key ones that we might be optimizing for is execution time, as in how fast does my application give a result back? And if you're writing a web server that's serving pages to users, that's probably really important, because if users wait too long for pages, you get a very high drop-off rate the longer they have to wait for a page to come back. But there are other things we can optimize for. We can optimize for developer time, i.e., if it takes less time for me to think about and do, but it runs slower, that may be an acceptable trade-off. And one of the third things we might optimize for, if anybody here, if anybody at the meeting has ever done a startup, is time to market, which can be different from the other two. I may work insane hours, but what I may be focused on is not how fast it runs, but getting a product out. so people can see it, so we're the first to market and we have an advantage, or even just proving the market exists at all. So how do we solve this complexity crisis? How do we allow ourselves to scale? Well, the simple answer is abstraction. So this is a fun control panel for the IBM 1401, and it's actually a control circuit about how the machine calculates Old English money. So this is, Old English money was pounds, shillings and pence, and there were 20 pence to the shilling. Sorry, there were 5 pence to the shilling and 20 shillings to the pound. So this was actually implemented in wires. Can you imagine implementing your logic today in physical wiring? You know, you want to have an if statement or a branch, you're going to physically wire those cables together. A few years later, and my father talks fondly about this, about punch tape and punch cards. And you used to write your code, punch it onto tape, and if you're at college or even university, what would happen is you would punch out your cards and you would send them away. And some hours or days later, they would come back with a syntax error. Right? Card 4 is incorrect. But then suddenly, we're working with the machine directly, and we talk about machine code. Right? We're writing machine code in a local environment. We're compiling it and running it. Each of these layers has sped up our cycle, right? Our time to actually from having an idea to implementing it. The next step is at the sideways step, where we introduce operating system, virtual memory. Suddenly, you know, multiple of us could run on the same machine. We were separated from each other, and it made everything look nice, right? It gave us certain protection and memory protection. If anybody remembers implementing code on old machines where if you did a null pointer, the machine crashed, that's a lot more fun. And debugging a machine that's dead is really painful. And then we have high-level languages. So high-level languages, you know, at the beginning, Algol, COBOL, and nowadays Java, Scala. Each of these is, you know, a language which allows us to write a fewer statements to execute more lower down. So one line in C may be 50 lines of machine code, and it probably writes better machine code than you do. And then we get on to VM languages. We abstracted again. So above C, we went, well, actually, I don't want to manage all the things. You know, my operating system already manages memory at a gross scale, but actually I can let the operating system of my program manage local memory, you know, and manage garbage. Because if you haven't if you've ever worked in Rust or you've worked in C, mentally keeping track of which objects are allocated and which objects are, who's responsible for freeing or releasing objects, is actually really painful. And when you get it wrong, bad things happen. So each of these abstractions has given us a power over the previous level. We can often do more quicker than we could previously. And Knut sums it up really well. The average programmer no longer has to manipulate the binary muck and works instead with hierarchies of abstractions, layers upon layers of code. i.e., most of the time when you're writing, you don't need to worry about the low-level details. And we have abstraction libraries as well. Let's be honest, libraries are great. I remember a time before open source software in the internet. And in those times, you know, you either wrote it yourself or you paid a lot of money to buy libraries that arrived on floppy disks. So if you take nothing else away from this talk, don't reinvent the wheel. Libraries are not always perfect, but they often save you a huge amount of time. They're stunning. But abstraction is great. But there's a problem. Fundamentally, functional programming is a lie. And hopefully that's received a few chuckles from the audience. But what I'm saying here is that it's not just functional programming. Let's be honest. Procedural programming is a lie. And yeah, let's go full hog. Assembly programs are a lie. What do I mean? Well, assembly programming is a lie. but it's a really useful lie. The code you write, even in assembly, is not the code that executes. For example, on a modern Intel processor, the assembly you write and the instructions you might think about when you're writing assembly code are not what's executed. In fact, that's converted to a lower level execution in microcode. But beyond that, when you write an instruction that says fetch an item from main memory, in the old days, you could actually calculate how many cycles that would take to execute. i.e., you could look at a loop in machine code and calculate how long each loop would take to execute. The problem is, with modern caches and modern operating systems, that's no longer true. Because when I say fetch this piece of memory, that piece of memory might not even be physically in the RAM anymore. It might have been put out to disk. And suddenly the operating system interrupts you, wakes up, does a disk access, loads it into RAM, and then pretends it was there all along. And this is really fascinating because it leads to things, this abstraction leakage leads to things like Heartbleed. So Heartbleed, suddenly I can access code that I'm not allowed to see because I can use the behavior of the cache to infer what stuff was there. Right? By executing an instruction that says fetch from a piece of memory that I'm not allowed to see, and it being executed out of order, it would seed my local cache. And I could tell, based on that, whether or not something was true. It's really fascinating when you think about it. So what about procedural programming? Again, it's not actually the truth. The code you write, forget all the assembly stuff for a second, but actually the code you write in C, especially if you use a modern C compiler like Clang, will use optimizers heavily. It will take your code and turn it and try and infer your meaning. And if you've ever tried to run a performance benchmark, you can actually see this sometimes when the optimizer is so smart, it just removes your code entirely because it decided it didn't do anything. And then you've got superscalar architecture. So the processor is executing your code all at once. You know, multiple instructions are scheduled at the same time. But the processor tells you a good lie, which is, for general purposes, it acts as if it run your instructions in order and only in order. And it pretends that the stuff that it did without you looking is not there. And it's great. And the same is true of functional programming. You know, all the other stuff about the assembly and execution and procedural programming is true. But we live in a mutable world. Every time you execute an instruction, stuff happens. You might think about your program in a purely functional way. But every time you return a tuple, every time you call an if statement, various things are happening behind the scenes. You know, behind the scenes, you're actually physically allocating objects. Those objects are going on the heap. Those objects might be garbage collected later. Even though you're perceiving the input as immutable, really, it's not just immutable. There's a bunch of what I would call non-functionals going on. Right? No program is truly pure. If it was, we would replace it with the answer. You know, once I've calculated something, if that's the answer, I don't need to replace it. I don't need to calculate it anymore. No matter how expensive it is to calculate, I can write it down and never have to do it again. So we do care about the world and interacting with data and all the rest of it. But we write our logic in a purely functional way because it's easier to reason about. And we care about the non-functionals. We care about how long it took to run. We might care about how much memory it took to run. Or how long it physically, how it performed, i.e. it might run in 10 seconds, might use 3 hours of CPU time. And the other interesting one is we might care about observability, and I'm going to come back to that point a little bit later, which is it's really useful to see what your program's doing, because if you're anything like me, one of the things I managed to do is turn coffee into bugs. And then I have to turn more coffee into working out why those bugs are there and and try and write down what I actually meant. So being able to infer what my program's doing is often really useful. Now let's talk a little bit more about functional programming. So what do we mean? What do I mean by functional programming? Well, I'm going to boil it down to the three key items. Right? A program is supposed to be total, i.e. defined for every input. Deterministic, it will always return the same value for the same input. And pure, the only observable effect is computing the output. Those seem really reasonable. So let's look at totality. So here's a nice simple function. At this point, I'd normally ask the audience, but I can't hear you. So, is this code pure? No, it's not. Why is it not pure? Because its result is not fully defined by its return type. With an empty string, it will throw an exception, right? Which is bad because exceptions leak. They destroy. The exception will propagate up the hierarchy. If I wasn't expecting it, then it will blow up my entire program. So we'll fix it. Right? We're going to use an option, right? That's a sensible thing to do. Now my program is total, right? Well, it's nearly total. And this is one of the problems. It's total because we say it's total. What are the valid values of user in this case? Well, the possible values are a valid user with a valid name or an empty name, or null. And then we look at option, it gets even worse. The possible values of option are some value, great, none, easy, null, and in fact, you can even get some null. I'm going to come back to null a bit later because it's a really interesting one, but nulls, like exceptions, are impure. And the JVM does not prevent you from passing it or returning it for any object reference. So that function looked great, but it's only pure because we said it was. So let's talk about determinism. So returning the same value for every input is great, right? It makes it really easy to reason about. And this is the key thing. Why do we do these things? Why do we do functional programming? Why do we do purity? Why do we do immutability? We do these things because it makes it easier to reason about the code. The problem is actually determinism in my example will cause a bug. So my example is I'm going to take two file paths and I need to join them together, i.e. a directory and a subdirectory. Now obviously what I need to do is you see them as strings, so I go string 1 plus slash plus string 2. That's great. Fully deterministic. Except when I run it on Linux. So I developed on Windows, I run it on Linux and it crashes. And it crashes because the path separator on Linux is the opposite way round to the path separator on Windows. So ask yourself, is this function deterministic? And I think it is. I think this is quite a reasonable thing to do. It's sort of breaking the rules, but it's not breaking the rules in a mean way. It's breaking the rules on purpose. But within the context of an execution, this code is deterministic. So, purity. Purity is great, right? Purity says that the only thing we're going to do, we have no side effects, nothing observable that breaks our system. But I don't know about you, but I don't write perfect code the first time. And when I do find a bug, and I will find bugs when I write tests, and we'll come on to tests a bit later, we will introduce bugs, and then we've got to work out what it is. Now, it's great at this level, right? I can test this function. I can test this function to destruction. But when this function is embedded in a huge hierarchy, I've got a really complex input object, fully immutable, fully functional, but it breaks somewhere down at the bottom. It may be very hard to see which bit of my huge data structure it was working on when it went wrong. Log messages are great, and I consider them, for most senses, pure, because you can't observe it from inside the program. Right? It might not be mathematically pure, but it's pure from the observability of the execution of your code. So this is a rule I think it's okay to break. Do be careful though. If, for example, you did x.length in the middle of your log message and your x was null, you'll find you never get the log message and you still get a null pointer. And trust me on this, it's really hard to debug when you're trying to run your code and for some bizarre reason, it never gets to the log statement. You're like, it must get to this log statement. I can see the line before, it's there, and yet it never outputs anything. And it's because your log statement null pointed. So null is fun. I generally say, don't use null. You shouldn't use null in general programming. And Tony Hoare, who actually introduced the concept of null into one of the first high-level languages, Algol, called it his billion-dollar mistake. He thinks programmers should have been banned from ever having it in the language. And the biggest problem with it is it's leaky. Now, there's a guy called Brian Catterall, and he talks about you want the program to fail at the point of failure. What do I mean by that? Well, let's say you call a library and it returns null. You might not notice. So you put it in a data structure, and then in your production system, some 6 hours later, after your logs have been purged and rolled and it's all gone, if you even log some of that stuff, it null pointers it. Null pointers because that null is in another data structure somewhere else. So the point at which your program failed is different from the point at which the error was introduced. And it leaks. So there's no way of trapping it. Unless you use the value, you don't know it's null. So, and as I say, option string, I've actually seen this where somebody had an option string where in one of the cases they returned null, and it was very confusing. So why would you use null? Let's start breaking the rules. Null is wonderful. The greatest thing about null, it is a zero allocation value. When I use null, I don't allocate any objects. Now, you might say none's the same, but what it means is when I have some of something, I've effectively created a wrapper around the value. I can effectively create an option by having a nullable field, right? Null means it's not there, value means it's there. And in fact, there is Kotlin uses exactly this. When you do X question mark in Kotlin, it uses null as the representation of value not there, and null is not allowed in the rest of your program. But it's great for high performance code. Right? Every time you wrap things, you need to think about it, and every time you wrap things, it has a performance impact. And my favorite example of this are two things: the LMAX disruptor pattern, if you've come across it, which is a very high performance ring buffer. And in fact, for those that have come across ZIO, the sort of purely functional library, they managed to use nulls all over the place in the code. Behind the scenes, though, right, you'd never see a null. But behind the scenes, to make it run as fast as it does, and it's incredibly fast, they cheat by using null as a marker value. So use null when absolutely necessary, and if you, only within a library, and do not expose it to the user. So those nulls should never leak out if you do use nulls. It's just one of the slightly annoying things because several of the Java standard libraries do use nulls for markers. So if you look at the concurrent collections, they do use null when they want to explain that a value is not there, which is, you've got to be careful when wrapping those because they don't behave exactly like the Scala ones. So if you're anything like me, you've been in multiple interviews in your career where somebody has asked you to write a blocking queue. The last time I did this, I wrote 4 lines that wrapped the Scala util blocking queue, and they looked at me like I'd gone mad when I explained I wouldn't write a blocking queue using wait and notify, which is what they were really asking, even if they paid me to. I did actually answer the question in the end because I could do it as well. But low-level concurrent primitives are horrible. If you don't believe me, go and read Doug Lee's book. Doug Lee wrote the concurrent collections in Java, which are awesome in their own way. But you'll notice he doesn't use wait and notify for most of his stuff, and you shouldn't either. But when he does, he's using a bunch of really low-level understanding of the JVM. The JVM, and in fact, in some cases, specific versions of the JVM exhibit certain behaviors. And there are certain guarantees provided by the Java memory model. So if you're going to do concurrent programming, use the collections that exist. Yeah. So to make this easier, I've written a little flowchart. Yeah. Should you write your own blocking queue? No. Even if your name's Doug Lee, you probably shouldn't do it. Right? This is just one of those things that you are not going to, except in very extreme edge cases, beat what's already there and make something better that's not full of bugs. The biggest problem with concurrent primitives is you will find that they work most of the time. And that's the worst kind of bug, where 99 times out of 100, you run your test, even in CI, and it runs fine. But once every 2 weeks, something fails in a weird way because of some ordering due to incret locking. The problem here is this stuff is really hard to reason about. And if you don't believe me, go and look at Java util concurrent. Look at concurrent hash map and the way it deals with size. You think size is a simple operation. In fact, it's incredibly complicated because of the concurrent buckets, and it uses a bunch of tricks to get around it. And the thing you'll notice when you look in those collections is practically every method has more comment than it does method, because comment defines exactly how it works, why it works, and what assertions you can make about it. So I know I say this is a talk about when to break the rules, and the answer is for low-level concurrent primitives, just don't. You will regret it later. So, one of my favorites, always write tests. Tests are great. If you're working in an organization, even if you're working for yourself, tests are wonderful. Whenever I've written a piece of code and gone, oh, it's so simple, I don't need to write a test. If I do actually write the test, I will find bugs. That's just the way reality works. And the thing is, it does two things. Especially when you're working in part of a team, it checks that both the code works as you expect, but also that it continues to work. When your tests are run as part of your continuous integration, it means that some subtle change by one of your co-workers fails at that point rather than in production. They are generally a great thing to do. So when do we not write tests? Well, actually, there's sort of two cases I've come across where it's not worth writing tests. So the first one for me is when it's a hacked script. Right? So if I'm quickly hacking something together to generate some data, so I had this a couple of weeks ago where I had something like a 200,000 line log file, and I needed to count various bits and pieces in it. And in fact, instead of even using a high-level language, I use shell script. And that's really untestable. But I use grep, and I use wc minus l, and I used unique minus c, and I used a regex, and it took me 10 minutes. And I could test it by eye, and it was awesome. But even when you're writing code that's doing a one-time thing, sometimes it's not worth the effort to write the test, because you just run it, you look at the output, and you verify by eye. But if something's running repeatedly or every day, or you expect it never to fail, you've always got to write the tests. The other time is if you're in a startup. So sometimes it's more important to get code in the hands of other people than it is for it to be perfect and stable. Something that breaks every second or third time but allows people to see what you're doing may be more important, especially in the early days, than making beautiful, stable, high-performance code. And in fact, if you look back at both Facebook and Twitter, they're hack scripts using PHP and Ruby that was hacked together to prove an idea and find a market. So sometimes it may be worth doing this. In fact, I know a story of a mate of mine who they gave a presentation to a client where it ran to the third page, then it crashed, and then they ran it again, and it crashed on the second page, and they were, they apologized to the client and switched to their slide deck. But in fact, the software had actually been designed to fail because they wanted the clients to see the slides more than the incomplete bits of software they had. And they could use that as a sort of discovery to what the clients were interested in. So just if you should generally write tests, but there's a couple of cases where it might not be worth it. So immutability. This is a no-brainer. Having come from a career of writing non-immutable code, when you discover it and you realize the beauty of it, you should pretty much always do it. And the beauty is you don't need to worry about what others are doing. So when you write C in a team, and I have an array, and I pass it to someone else, and they need to keep a copy of it. Do they keep a copy of it? Do they keep the original? Who's responsible for freeing the memory? Now, if you get it wrong, it'll either crash or not fail and leak memory. But also, when you're dealing with multi-thread environments, when you've got multiple cores, multiple threads, immutable data means that I don't get data corruption. I don't get visibility issues. It is a good thing. You should do it. But let me tell you a dirty secret. This is the cons operator. Effectively, this is the colon of the Scala immutable list. But it's got a nasty secret. And the nasty secret is this. It's got a var on the tail. And this sounds insane, right? Except there's a good technical reason for doing it. So the problem is, if I've got a list, I can only iterate from the head to the tail. So when I do map, I need to iterate from the head to the tail, building a new list. But I can only append to a list on the head, typically, right? And I've got an immutable list, and I can effectively cons an item onto the front. Great. So I can cons an item onto the front. But if I do that whilst traversing a list, what I end up is a list in the reverse order. So what I then need to do is traverse it again, creating a second new list, which will now be in the right order because I've just reversed the second list. So Scala pulls a trick on you. When you're using a list builder, what it does is it edits the tail. The reason this works is because it only ever lets you see it once the list is built. It only ever lets you see a list once it is built. And in fact, as a little second sneaky line here, you must call, and a comment, which says, you must call release fence once the list is visible. And it's really important, because that is the thing that guarantees that that var is flushed to main memory and visible. But it's only mutable inside the Scala package. So in fact, the Scala compiler and the Scala collections use this to do their thing. So what I've done is I've built an immutable collection using mutability. And it's a really neat trick. And you'll see that a lot. If you open up the Scala collections, you'll see this trick pulled quite a lot. But it is incredibly dangerous. As in, a subtlety here breaks. This release fence didn't actually exist at some point, and it could subtly break your users. So if you do use immutable data structures and externally immutable as a minimum, from your point of view, Scala util list is immutable, and that's fine. But there are really useful non-immutable data structures. One of my favorites is concurrent hash map, and in fact, it's a little naughty in more than one way. So the first thing it does is it will return null, but it gives you a bunch of utilities for dealing with concurrency in a way you can't do otherwise, or the way that's hard to write. So you can say put if absent, which in a thread-safe way will create the object and return it to you. But if two people try and do it, one of them will get locked and only one will create the object. There's a whole bunch of utility levels down there, and it's great for that kind of stuff, but you've got to use it carefully. The other thing, as I've said before, is if you're going to write mutability inside your library, be really, really careful, because it's actually really hard to get right. So, a last couple of items before I finish. Efficiency. I'm hoping some of you have come across this wonderful chart. I will share the slides with you all after the talk. But if you haven't come across this before, this is one of my favorite charts, and I have it on my wall, which is how long can you work on making a routine task more efficient before you spend more time on it than you save over 5 years. So if I save myself 5 minutes on this task, and I do that task 50 times a day, I could spend 9 months out of those 5 years automating the task, and I would still save time. So this is wonderful, right? This gives you some clue about how long you should spend. And I think if I can spend, a few hours automating something that saves me 5 minutes a day, it's great. I can make myself much more efficient. But efficiency is a funny thing. As Knut said, premature optimization is the root of all evil. So, a lot of people start optimizing far too early. You should only optimize if something's slow. Let me give you an example of something I don't bother optimizing. 3 AM scripts. If I've got a script running on a cron job that runs every night, it doesn't really matter whether it takes 30 minutes or an hour to run, or 2 hours. As long as it's done by the time I get in the morning, it's irrelevant. So the key thing is their clarity and debuggability rather than being clever. And migration scripts, things that you only run once. It doesn't really matter if my database migration takes 4 hours. Yes, I could write a version in 3 days that runs it in 10 minutes, but I've lost 3 days instead of writing an hour's script and then running it for the afternoon. And this is true for reactive as well. So generally avoid blocking. It makes things slower and it reduces your parallelism. It's a good thing. But when you do write blocking code, it's really simple. Get A from the database, get B from the database, add A and B, put B, put the answer back in the database. Right? It's easy to reason about, it's easy to debug. And command line apps. So often they don't need to be fast, they just need to work consistently. So, in conclusion, computers are stupidly powerful. We have tons of memory, We have very fast processors. We have very fast disks. You can be stupidly inefficient. In fact, I suspect my laptop spends more time waiting for me to type anything than it's ever done doing actual work. Choose what you optimize for. Computer time, great. We like programs that run fast. But the key one for me is developer time. And what that means is it is a choice generally. And I found if you look back at all these examples and all the other examples I can think of, it's generally a choice between clarity and speed. I can write it simply or I can make it fast. But when I make it fast, it tends to be harder work. I have to do more work. You can break the rules. Each of these times we're breaking the rules, what we're doing is we're breaking the abstraction. We're looking, as I say, inside the sausage factory. You know, we're looking under the hood and going, well, I know really that I can represent the value as null, or I can add a log statement, or I can, you know, just block and wait for the result to come back. Each of these choices is a trade-off. And what you should be doing, and the key thing you should be doing, is making an active choice. Follow the rules for functional programming. Follow the style guides. Follow the best practices. But when you decide to break the rules, decide to break them. But when you do, there should be a big fat comment that says, here is what I'm doing, here is why I did it, here is the decision I made, because you'll thank yourself later. Because often you end up with a really complex bit of code to do something very clever. My personal example is Scala's list has a filter function, which I made run significantly faster with significantly fewer allocations. But the original code was 2 lines, and you could look at it and go, it's correct. My code was 20 lines, and you had to stop and think about it every time you looked at it, because it was effectively representing a state machine about what state I was in whilst I was traversing the list. So make active choices about when to break the rules. But don't be afraid to break the rules, but break them by choice. As Terry Pratchett sums up really well, that's why the rules are there. So you think before you break them. So that's the end of my presentation. I hope you've enjoyed it. I hope I've met some of you when I was at Scala UA.
Thanks, Rory, for the talk.
You're very welcome.
Yeah, it was enjoyable even the second time.
Wow.
Do you have any questions? Do you have any questions apart? There's no one on the list. No one wants to ask anything. Maybe I'll just ask same thing I asked you before about the documentation of these things. Do you have anything else to recommend besides commenting these trade-offs?
I think, yeah, as I say, generally try and not do it at all. But I think you have to document and prove. So the classic for me is optimization. If you're going to optimize something, you must measure it. Right? If you don't have a benchmark that says this code is slow, the code might not be slow at all. And often, if you've ever done profiling and optimization, you'll find that the code you think is slow is often not the code that's slow. So, especially with stuff like optimization, document first. You know, document what you're doing, but make sure you're actually doing something useful. I spent a lot of my career wasting time being clever and optimizing the wrong thing.
All right. So then I wish you a nice evening, and thanks again for joining our meetup.
And to all, and enjoy the pizza, and hope to see you all soon.
Cheers.